Have you ever looked up at the night sky and felt a sense of wonder? I certainly have. The universe is a vast and astonishing place. It is filled with billions of galaxies, each containing billions of stars. And around those stars, there are countless planets, moons, and other celestial bodies. We have learned so much about our cosmic home. We understand how stars are born and how they die. We have mapped distant galaxies and even listened to the faint echoes of the Big Bang itself. But for all we know, there is so much more that remains a complete mystery. One of the most mind-bending of these mysteries is the idea of a white hole. To truly appreciate the strangeness of a white hole, we first need to understand its more famous sibling. We need to talk about the black hole. Imagine a star, much more massive than our own sun, reaching the end of its life. It runs out of fuel and collapses under its own immense gravity. This collapse is so powerful that it crushes the star's matter into an infinitesimally small point, a point of infinite density called a singularity. Its gravitational pull is so immense that it warps the very fabric of space-time around it. But a black hole creates a bottomless pit, a well from which there is no return. There is a boundary around this singularity known as the event horizon. Once you cross the event horizon, you would need to travel faster than the speed of light to escape. So a black hole has two key parts we need to remember. There is the singularity at the heart, a point of infinite density where our physics fails. Think of it like the edge of a waterfall. At some point, you cross a line where the water is flowing faster than you can possibly paddle. The event horizon of a black hole is just like that, but for space-time itself. Inside the event horizon, the nature of space and time is warped in a very strange way. All possible paths point inwards to the singularity. You can no more avoid it than you can avoid next Tuesday. Even light, the fastest thing there is pulled inexorably inward. From our perspective, we can only see the darkness where light has been forever trapped. What happens if we take these same equations and simply reverse the flow of time? In physics, many fundamental laws are time-symmetric. When you perform this mathematical operation, something extraordinary emerges from the theory. You get a region of space-time from which matter and energy are violently expelled. This is the theoretical birth of the white hole. It is the exact mathematical opposite of a black hole. It suggests a fundamental symmetry in the universe, a balance between cosmic sinks and cosmic fountains. Let's try to picture what a white hole would actually be like. If a black hole is a bottomless pit, a white hole would be an eternal mountain. This material would erupt from the central singularity, now acting as a source rather than a crusher. Unlike a black hole, which is invisible, a white hole would be intensely, blindingly bright. However, light trying to leave would be redshifted, appearing to fade and freeze in time. We would expect to see them, yet when we scan the skies, we see nothing that fits this description. This lack of evidence is the biggest problem for the idea of white holes being real. Stephen Hawking showed that black holes are not completely black after all. They should emit a faint glow of particles. This is now known as Hawking radiation, and it means black holes can evaporate. This creates the black hole information paradox. If information can never be destroyed, where does it go? Perhaps at the final moment, the black hole transforms into a white hole, releasing its stored information. Some physicists wonder if our universe's Big Bang could be explained by a white hole. What if our entire observable universe is material that erupted from a universe-sized white hole? This suggests a grand cosmic ecosystem where new universes are born from black holes. Our universe would be the child of a black hole in another cosmos. The most profound difference between black and white holes is about time. Our universe has a clear direction for time. We never see broken pieces spontaneously assemble and leap back onto the table. This is the arrow of time, linked to entropy. Black holes fit perfectly, taking ordered things and crushing them into chaos. A white hole would violate this fundamental law, spontaneously decreasing entropy. The story begins with Albert Einstein, who published general relativity in 1915. Karl Schwarzschild found the first exact solution while serving on the Russian front. His solution contained something strange, the mathematical seed of the black hole. Buried within was not just the black hole, but its time-reversed twin, the white hole. The quest to understand white holes pushes the boundaries of what we know, forcing us to confront the biggest questions. What is time? What happens at singularities? Is information fundamental? So the next time you look up at the stars, think about the unseen mysteries they hold. The universe is under no obligation to make sense to us, but it has given us a mind to try. The journey of discovery has only just begun.